So that kind of tells you what sort of forecasting errors you could tolerate. For example, let me go back to sales. Let's say my forecasting or error of net sales is plus or minus 10%. Okay. If I get on the negative side, 749 times 10% of my original net sales. No, I shouldn't do that. Oh, I just need to multiply that by 10. So each 10% increase or decrease in net sales is going to increase or decrease my MPV by 74%. Oh, that's a big number. Okay. So this was originally 143. If I go on the lower end of the forecasting error, that's going to decrease it by a factor of roughly 4. Let's round it up to 75%. That means I'm going to go down to about 35,000 or so. I'm not that comfortable at 35,000 anymore, right? In fact, let me go back to 100, 600. Copy. Values. I mean, it's still big, but PI now is only what 115, okay, compared to what it was before. Oh, oh, this is if I do 10% less. I mean, I would still accept it, but I'm not that comfortable anymore. My MPV is only about 3.5% of the original investment cost. And at this point, I haven't even talked about possible errors on other inputs. This is only the effect of NPV. So that's the role of sensitivity analysis. Which one of these variables has the most effect on the estimates? If I find out that 7.5 elasticity is high, if that is that high, then I need to go ahead and figure out, okay, is there a better way that I could reduce my forecasting risk? It kind of highlights. The second type of analysis is called scenario analysis. Scenario analysis recognizes that forecasting errors of different inputs are possibly correlated. Okay, if I'm estimating the sales much higher than they are, that probably means I am also estimating the costs much higher than they are. But in sensitivity analysis, I'm keeping that fixed unless I do it in such a way that I relate it to some sort of cost function. But even there, we have possible errors similarly with fixed costs. those costs may be correlated themselves, and overall economy, what have you. And scenario analysis basically says find some reasonable best and worst case scenario, and evaluate the um, MPV under these scenarios. Based on our statistical model, we could attach some sort of possible forecasting error on each input, and based on those, we could create these. So I'm gonna do a simple case. Suppose each of our inputs, sales, variable cost, MP, fixed costs, and change in net working capital are subject to plus or minus 10% forecasting risk. The way you calculate in the best case scenario, for variables that affect NPV positively, such as sales, use plus 10% of the base. For variables that affect NPV negatively, use negative 10% of base. Variable costs, fixed costs, and change in net working capital, they all affect NPV negatively. If I have more net working capital, even though I'm going to return it back at the end because of discounting, NPV is going to decline. You do exactly the reverse for the worst case. For positive variables, use negative 10% of base. And for negative variables, use positive 10% of base. So let's kind of do this here for this example. Let's go back to original 600,000. All right. And I'm going to use plus or minus 10% of that variable cost percentage. So let's do the best case scenario. 10% of that is 660. And that's going to be 49 and a half. I'm sorry, not 49 and a half. Since it's negatively 40 and a half, I'm taking 10% of the 45%. That's going to be 55%. And I'm going to make this 270. Okay. So my best case NPV is 348,968. Now I'm going to do my worst case. That's going to be 540. That's going to be 49 and a half. And that'll be, no, I was wrong. This should have been 45,000. So MPV is going to put in 381. 330. As you can see, my worst case MPV is negative 220 in thousands of dollars. Of course, this example is simplistic. I forced all forecasting errors to be the same percentage. That will never be the case, but based on your statistical model of estimating these, you're going to attach reasonable confidence interval in a sense. We typically do a 95% confidence interval. For the positive variable, use the upper end of the confidence interval. For the best case, for negative variables, use the lower end and switch the roles for the negative variables. If a project gives you a positive MPV, even in the worst case scenario, your confidence in profitability of that project goes up. Ideally, you would actually come up with a probability distribution of forecasting errors that are joint, and you would do what we call a Monte Carlo simulation, but that's the topic of an upper level finance courses. I'm not even sure that we covered it in Finance 301. If I was teaching it, I would cover it, but I don't know what the current professor is doing. But if you had an MSF class, Master of Science in Finance, I would definitely use it in that class.